So the method of proof by mathematical induction says you consider a statement in the form of for all n elements of the integers with n greater than or equal to a, where a is an element of the integers, a property p of n is true. So for instance, well, we'll go through some for instances today. And to prove such a statement, you've performed the following two steps. We have two steps. One is called the basis step, and the other one is called the inductive step. The basis step, you show that the property is true for n equals a. Now, n, you'll notice that in this, it says n is greater than or equal to a. So a is essentially the initial value that you look at. So a is our initial value. Come on, dot that I. So a is our initial value. You first check that the statement you've made is true for the initial value. Step 2 is the inductive step. In the inductive step, you assume that the statement is true, or your property, whatever it is true for P of K. And using the truth of P of K, you use that to show that P of K plus 1 is true. The assumption that P of K is true, we call that the inductive hypothesis.
How do I fit this thing in here?
You're going to use the inductive hypothesis every time you do a mathematical induction proof, unless it's actually not necessary to do the mathematical induction proof. Hypothesis. Okay. So step 2 says the inductive step, show all for all k elements of the integers such that k is greater than or equal to a. If P of k is true, then P of k plus 1 is true. This is achieved by supposing that P of k is true, where k is a particular but arbitrarily chosen integer, such that k is greater than or equal to a. This is called the inductive hypothesis. Then show that P of k plus 1 is true. So, in a way, what you're doing is this. You have a first value, and that first value is the integer a, whatever a is. So we have a value a. And you show that that first value, P of a, that whatever that property is, you show that this is true. And because you assume that k is any value greater than or equal to a, it could be a. So if k is a, and you know that a is true, because the assumption that P of k is true then gives you are able to prove that P of k plus 1 is true. Sophus, you may not take those. I already told you that.
I just want to look at it because I missed the first part.
So the assumption that P of k is true leads directly to being able to show that P of k plus 1 is true. Means that, well, for one thing, it's going to mean that if a is true, P of a plus 1 is automatically true. Likewise, if P of a plus 1 is true, then P of a plus 2 is true. And then P of a plus 3, P of a plus 4. So it's like you've got these things all sort of lined up. And just showing that the first value is true, and that assuming that any given value in here is true leads you to the next value being true, sort of knocks all of these down at once. It allows you to prove that it's true for every value of k greater than or equal to a, just by doing that. How do we actually go about it? So this is the process. You're going to need to remember the inductive hypothesis because we use it a lot in the proof. It comes up every proof. So let's look at a particular example. Excuse me. So, the sum of the first n integers. The sum of the first n integers, when you start with 1 and you add up 2 and 3 and 4 and 5 until you get to whatever n is equal to n times n plus 1 over 2 for all n greater than or equal to 1. Well, it says, you'll notice here, greater than or equal to the positive, well, not greater than or equal to. N is an element of the positive integers. So that means that n is 1 or 2 or 3 or any of the positive integers, but it can't be 0. So when it starts at, when you're given for all n element of the positive integers, that means your initial starting point for that is going to be 1. This is what A is. So, how do we do this proof? Well, first of all, we need to establish what the property is. So that's our first step in the proof. We always start a proof by saying proof. It also doesn't hurt to identify what kind of proof it is. This is a proof by mathematical induction. Okay, so this is our proof by mathematical induction. And first we establish the property. So we say let P of n be the property that 1 plus 2 plus 3 plus so on till we get to n equals n times n plus 1 over 2 for all n element of the positive integers. So this is our property, and I think I'm going to fix up that plus sign. It's just messy. Okay. For all n element of the positive integers. So we've established what the property is. Then what we need to do is the basis step. That first step where we show that the property is true for the first value of n, the first value that n takes. So here we show P of 1 is true because 1 is our first value here. Now, well, what does that mean? Well, with our particular one, remember on the left-hand side of the equation, we have 1 plus 2 plus 3 plus all the way up to plus n. In this case, n equals 1. So what is this equal to in the case where n equals 1? When n equals 1, what does this entire side equal? Not sure I caught that. What does our left-hand side equal? If we only have n equals 1, so we know that n equals 1, right? But what's all this got to do with it? If n equals 1, what happens to all of this stuff over here? Sophist, do you know?
If n equals 1, that means it's just 1.
It's just 1, that's right. So we just reduce down to 1 on the left-hand side. So in our basis step, we know n equals 1. So our left-hand side is simply going to be 1. And our right-hand side is, let's see, then our right-hand side, the equation says n times n plus 1 over 2. Well, n in this case is 1, so that's going to be 1 times 1 plus 1 over 2, which equals 1 times 2 over 2, which is 2 over 2, or simply, how does that? 1, which is what we need it to equal to. So if we get this, we have shown that the property is true for n equals 1. So we can write that down and then say, thus, P of 1 is true. So in this case, our basis step has just been proven. Now, we need to, let's see, what's our best way of writing that? Show that for all integers greater than or equal to 1, if the property is true for n of k, for n equals k, then it is true for n equals k plus 1. So show for all k greater, for all k greater than or equal to 1, but which is essentially the same thing as for all integers k that are positive integers, because they would have to be greater than or equal to 1. If the property is true, so if P of k is true, then P of k plus 1 is true. This is the inductive step. So this is where we are right now. So now, this means we suppose or assume, so thus we assume and we're going to assume the property is true for k. So what we're assuming is 1, let's make that a little bigger, 1 plus 2 plus 3, all the way until we get to plus k equals k times k plus 1 over 2. We assume that this statement is true. Do we know it's true? We don't know it's true yet, but we're going to prove that it's true. So we assume that this is true for all k elements of the positive integers, or for all integers k greater than or equal to 1. Now we must show that one plus 2 plus 3, we need to show that the next value, k plus 1, is true, using only the fact that our first value is true and that this is true for k. So up to k plus 1 equals, this is where we're trying to go, k plus 1 times k plus 1 plus 1 over 2, which we can simplify as k plus 1 times k plus 2. By basic algebra. Now, a note on basic algebra. I have sent out a document called the Algebra Laws document. And sometimes you might want to refer to the algebra laws individually, but a lot of the time you can just say, whenever you're referring to something happening in that document, you can just say basic algebra now. Before we needed to say things like the zero product property or theorem 12 or field axiom 2, the commutative laws, any of those things. You don't need to refer to them individually like this anymore. We can just say by basic algebra now. We're simplifying that down. Okay, so this is what we need to show. How do we do that? Well, we sort of start out. We're going to go say then, and then we're going to write the equation. We use what we know to prove this statement. So we're going to start out with 1 plus 2. Honestly, we could go from one side to the other or back again, however we want to do it. But sometimes there's always an easier side to make and use the inductive hypothesis with. Of these two sides of the equation here, this left-hand side is much easier to use the inductive hypothesis with. And that's because it's got this part right here, which is part of the inductive hypothesis. So we'll start with that side. 1 plus 2 plus 3 plus all the way out to plus k, and then plus k plus 1. Well, if we take aside this 1 plus 2 plus 3 plus out to plus k, what do we know that's equal to? By everything we've done thus far, what do we know that that is equal to?
1.
That's not equal to 1. It's only equal to 1 in the basis step when n equals 1. But now we don't know what k is. We don't know what k plus 1 is. We just know that k plus 1 is 1 beyond k. But by the inductive hypothesis, the assumption we assumed to be true, right up here at the top, we say that 1 plus 2 plus 3 plus all these values up to plus k is equal to k times k plus 1 over 2. That's our assumption. And therefore, we can make that substitution because that is what we have assumed to be true. So 1 plus 2 plus 3 plus up to plus k, we can assume to equal k times k plus 1 over 2. But we still have this k plus 1 term here. So that needs to remain. This is plus k plus 1. We can say this by, and I said you were going to use this a lot, by the inductive hypothesis. Say that again. Tara?
Sorry, I didn't notice my speaker was on.
Okay.
Just having a shot.
Okay. All right, so we can do this by the inductive hypothesis. So now we have our left-hand side here of our equation. We're going to keep lining up our equal signs. And what we know where we want to get to. We want to get to this point over here in the equation. We want to be able to say that this equals k plus 1 times k plus 2 divided by 2. So now, well, what can we do? Well, this side we have a fraction over 2. It might be helpful if we could add our k plus 1 to our fraction over 2. And for that, we could multiply this by 1, because anything times 1 is itself. So I'm going to keep parentheses around it. So right here, I'm going to leave this part alone for a little bit so I can adjust this so I can add it to the other part. So this will be k times k plus 1 over 2 plus 1 times k plus 1. See, I haven't changed the value at all. Okay. Then this equals, well, I'm going to change the 1. 1 is also equal to 1/2 times 2, right? So I'm going to change 1 into 1/2 times 2 because that's an equal value. So this is k times k plus 1 over 2 plus 1/2 times 2 times k plus 1. And then I'm going to join my 2 times the k plus 1 together, and I have my 1/2, and I can bring them all together into one fraction. So this is k times k plus 1 over 2. Then I have plus, this is all over 2, 2 times k plus 1. And now because I have these two fractions, they both have the same denominator of 2, I can join those two fractions together. So there is k times k plus 1 plus 2 times k plus 1 over 2. Now, here, I'm really close to where I want to get. You'll notice I have a k plus 1 here and a k plus 1 here. By the distributive property in our algebra laws document, you can then rewrite this. I've got a k here out in front and a 2 out in front, so I can write this as k plus 2 times k plus 1 because they both have that component of the k plus 1. And actually, this is very close to what I wanted to get. I wanted to get k plus 1 times k plus 2. So by the commutative laws now, I can just swap their positions. So this is k plus 1 times k plus 2 over 2. And all of these steps that I've just done. So remember, in the old classes, we always had to give reasons. But all of these things in here, they were all done by basic algebra. They were all done by things in the algebra laws document. So I can just say by basic algebra. That covers everything that's happened in the last several steps. So we're sort of simplifying the explanation process at this point. All of those steps occurred by basic algebra. And this is where we wanted to end up with, so we just say this is what was to be shown. And we end our proof. You end your proof with a little tiny square in the bottom. And that says that we completed that. So what that means is we proved that this theorem was true for the first value, for 1. It's a true statement. We assumed that it was true for the kth statement, and using the assumption that it's true for the kth statement, we showed that it had to be true for the k plus first. And that means if it's true for the first, it's true for the second. And if it's true for the second, it's true for the third. And no matter how far along that line of numbers you go, you continue to prove that it's true for the next value. And in this way, you prove an infinite number of statements with one proof. That's the process of a proof by mathematical induction. So this is a very powerful thing. And it also means that now that you've proven this statement, you can easily go ahead and use the results of it. So, for instance, say you needed to know, for whatever reason, 1 plus 2 plus 3, all the way up to, say, plus, we'll say 50.
Wow.
Now, do you want to sit there with a calculator and put all of this stuff in? Not really. That doesn't sound like a good time. But using this theorem of the sum of the first n integers, you know that you can say that this is equal to 50 times 51 divided by 2, which is 25 times 51. And we can do that multiplication quickly. 25 times 51 is 525. Oh, sorry, that's a 0. 2, 5. Oh, sorry, 10. Thank you. I'm going too quickly for myself. We add, so we've got 5, 7, 2, 1. And that means that this equals 1,275. And we know that that's true without sitting down and going through and typing 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to plus 50. So we've just reduced something that can be incredibly tedious to something that's relatively quick and easy. But what if we have a variation on that? Say we want to find 2 plus 4 plus 6 plus 8 all the way up to, say, we'll go up to 50 again for whatever reason, except this is a different calculation. Can we use our sum of the first n integers? Well, remember that the sum of the first n integers, it needs to be of this form. It needs to be 1 plus 2 plus 3 plus 4. Is there some way we can make 2 plus 4 plus 6 plus 8 look like that? Sophus.
Even though I haven't been here, I'm guessing it's, look. So right here, 1 plus 1 is 2. 2 plus 2 is 4. 3 plus 3 is 6.
Okay, so what can we do to change this into a form that looks more like what we need for our sum of the first n integers? They're all doubled, right?
Yeah.
So what if we remove a 2, if we use our distributive law and we remove 2, or a power, divide each one by 2 by pulling the 2 out. So if we use the distributive law, we know that 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. How high up will we go? 2 times what equals 50?
25.
25, right. So we can rewrite 2 plus 4 plus 6 plus 8 all the way up to 50 as 2 times 1 plus 2 plus 3 plus 4 up to 25 instead. And so this, now we can use that property. We keep our 2 out in front. And now it is 25 times 26 over 2. Well, these two 2's here and here, they're going to cancel one another out. We have a 2 over 2, which is 1. So we'll simply be left with 25 times 26, which is so we have 0, 3, 15, 1, 4, 5. Am I doing this right? 3, 12, 15, yes, 0, 0, 1, 4, 5, okay, 0, 5, 6. So 650. And that's times, oh wait, we got rid of the 2. So this equals, yes. So that equals 650, I guess. Yes. Oh, I went to something different there. So that goes to 650. So that again simplifies the matter a bit, so we don't have those 25 terms to throw into a calculator and add up. What about something like this? Nope, not like that. 4 plus 5 plus 6 plus 7, all the way up to plus, we'll say 22 for no particularly good reason. So if we have something like this, is it of the right form to use our sum of the first n integers? Can we go ahead and use our sum of the first n integers on this example?
Yes. Couldn't you just do it and just subtract 6 at the end?
Right. So what we're going to do is we're going to add 6 and subtract 6. So when we add 6, we'll do 1 plus 2 plus 3. That equals 6. And then we continue on with what we had. And then at the very end, we're going to subtract that 6 away again. So we haven't changed the value. But we know that this first part is going to equal 22 times 23 divided by 2. And then we subtract our 6. So the 22 divided by 2, that'll be 11 times 23. Sophus, what's 11 times 23?
11 times 23. 11 times 23 is... I can do it.
Okay. Sophus is really good with his 11s.
Yeah, but when they get higher than 10, I'm a bit...
Yeah.
No, when they get higher than 12. 12 I can do in my head. 253.
That's right. So we have 253 minus 6, and that will be 247. So, again, the sum of the first n integers can be applied in a lot of different situations. You just need to make sure in certain cases you need to adjust what you're doing. So when they're multiples of 1, 2, 3, 4, or when they take off like a beginning section or something, that you're starting at the right place. And you can just do that by little adjustments. Here we subtracted 6. Here we used the distributive law to remove a 2 from each of those values. So you will have some examples to work on using this. Okay, so I think I want to go through the process of mathematical induction again. Let's see. I forgot to make sure that we don't have the binomial theorem here, and I think we don't. No, we don't. Okay, so stop. Sit. Thank you. Okay, so I want to go through an example just to remind you of the process of mathematical induction. So I'll clear this out. This is going to be from the homework section, section 4.6 on page 56. This is number 12. It says prove that if we get rid of 1 cent coins and replace them with 3 cent coins, and we would be able to cover all monetary values greater than or equal to 8 cents. So, and using only 3 cent coins and 5 cent coins. So, what we're going to do this time this is number 12. So we're going to prove that if we got rid of a 1-cent coin and replaced it with a 3-cent coin, that using nothing more than 3 and 5-cent coins, we could get every value higher than or equal to 8 cents. So we'll say proof. And this is by mathematical induction. So first what we're going to do in the proof is we're going to show, first we establish what our property is. So we say, let P of n be the property that n cents can be formed using only $3-cent and 5-cent coins. For all n greater than, or well, n element of the integers, because our coin values need to be integers, such that n is greater than or equal to 8 cents. Okay, so what is our basis step? What is our initial value? What is the first value that n can take? 8, that's right. So we need to first show that we can use 3 and 5-cent coins to make 8 cents. Well, that's pretty easy. So first we show P of 8 is true. We could say, notice that $0.03 plus 5 cents equals 8 cents. Basis step is done. So, thus, P of 8 is true. Now, we need to show that for all k elements of the integers such that k is greater than or equal to 8 if P of k is true, then P of k plus 1 is true. So, we assume, in this case, that k can be made, or k cents can be formed using nothing but 3-cent and 5-cent coins, whatever k is. We must show, using nothing but our assumption that k can be formed by 3-cent and 5-cent coins.
It's wrong. How can you make 9 with 3 cents and 5 cents?
Easy. So
Wait,
we
what?
must show that k plus 1 cents can be formed using nothing but 3-cent and 5-cent coins. So you say it's wrong, Sophus. 8 cents. 8 cents equals what?
8 cents equals 4 twos, 2.
Well, no, only using 3s and 5s.
A 3 and a 5.
So 3 cents plus 5 cents.
9 cents, however.
9 cents equals
There's no
what?
1 cent.
True. But it equals, what's another way we can equal 9 cents using only 3 and 5 cents?
3, 3, and 3.
3, 3, and 3. So 3 cents plus 3 cents plus 3 cents. Okay, what about 10 cents? How can we form 10 cents using only 3 and 5 cent coins?
5 plus 5.
5 plus 5. Now for 11 cents, we do, well, we replace one of our 5s by 2 3-cent coins. So we would have 3 cent plus 3 cent plus 5 cents. And then we have 11 cents. What about 12 cents?
3 plus 3 plus 3 plus 3.
Right. So does it look like we can keep doing this? It looks like this is possibly feasible, but what is the pattern we set up? When we have a 5-cent coin, we replace it then with 2 3-cent coins. So the next one up, because 5 cents, 6 cents is the value of 2 3 cents, and that's one more than 5. Then if we have 3 3-cent coins, we replace those with 2 5-cent coins, because the next value up from 9 is 10. But once again, we have a 5-cent coin, so we can replace the 5-cent coin with 2 3-cent coins, and then we replace the other 5-cent coin with 2 3-cent coins. And then we once again have our set of 3 3-cent coins that we can turn into 2 5-cent coins. So we've got 13 cents equals 3 cents plus 5 cents plus 5 cents. So it looks like as long as we've got a 5-cent coin, we can get the next value up just by adding, just by changing it into 2 3-cent coins. And as long as we've got 3 3-cent coins, we can get the next value up just by changing it into 2 5-cent coins. So this is our process, but this stuff right here, this is not the proof. This is us figuring out how the proof is going to work. So we need to make sure this stuff is not in the middle of our proof. So I'm going to erase it. But now we know how we're working.
How did you get 12 cents? 4 threes? How did you get
4 threes.
11 cents?
That would be 2 3s and a 5.
So it's true. Every number.
It is true. Over 8 cents. You can't get 7 cents. You can get 6. You can't get 4.
You can get 5.
You can't get 2. You can't get 1.
You can get 5.
Right. But you can get anything over 8. Okay, so we are assuming that K has is only made up of 3 or 5 cent coins. Now, if you haven't been in the class, one of the things that we do when we have different possibilities is we do what's called a division into cases. And in the division into cases, we say, well, it's possible we have one thing or another. Well, with K cents, we know that either we have a 5-cent coin or we don't have a 5-cent coin. And so we can divide our proof into the possibility that either we have a 5-cent coin in order to make K. Can you guys calm down, please? Either we have a 5-cent coin in order to make K cents, or we don't have a 5-cent coin. And we need to show that regardless of whether we have the 5 cents or we don't have the 5 cents, this proof is true anyways. So we're going to divide into cases. So first we say, just calm down with that. Either K cents contains a 5-cent coin or it doesn't. Sophie's quiet. So either it contains a 5-cent coin or it doesn't contain a 5-cent coin. So then we say case 1. K cents contains a 5-cent coin. So in this case, notice that $0.03 plus 3 cents equals 6 cents, which is 1 greater oh, my case doesn't have an E on it, which is 1 greater than 5 cents. Thus, if K cents contains
What? K K cent?
Yeah, we don't know what K is. A 5-cent coin, then we can replace the 5-cent coin by 2 3-cent coins to get K plus 1 cents. So we have shown that we can get K plus 1 cents if we have a 5-cent coin. Now case 2 says K cents contains no 5-cent coins. Now what do we need to do when we don't have any 5-cent coins? How do we get 1 coin greater? What is our substitution then? We have a bunch of 3-cent coins, but we trade in how many 3-cent coins for what? What's our next value up? So we were able to go from a 5-cent coin to 6 cents using 2 3-cent coins, but now we just have 3-cent coins. How can we get 1 more cent?
We can't.
Yes, we can.
5-cent coin.
So we changed 3 3-cent coins into 2 5-cent coins, which means that we need to have at least 3 3-cent coins. How do we know that we must have at least 3 3-cent coins? There's something that makes it so that we can't have any less. Since we have no 5-cent coins to make up K, it's only made up by 3-cent coins. And we have a guarantee that we will have at least 3 3-cent coins. Because if we only have 2 3-cent coins, what's the value? What is 3 cents plus 3 cents?
6 cents.
6 cents. And what is our proof for? Values over what?
8 cents.
8 cents. So we must have at least 3 3-cent coins. We can't have less than 3. If we have no 5-cent coins, we must have at least 3 3-cent coins. But we need to write that into our proof. So if our K cents contains no 5-cent coins, then we must have at least 3 3-cent coins. Since $3 plus 3 cents equals 6 cents, which is less than 8 cents. And our proof is for values of 8 cents or greater.
Give me my pencil.
Guys, stop fighting, please. Let's write that better. Of 8 cents or more. So now that we've established we have at least 3 3-cent coins, notice that we can replace 3 3-cent coins for with 2 5-cent coins. Oops, I want to write that as a number. To get 1 cent more. Sophia, stop. In this way, we can get k plus 1 cents when we started with k cents. Okay, so then we can say, in both cases, we have made k plus 1 cents out of only 3 and 5 cent coins. This is what was to be shown.
That is long. I know. Proofs are long.
And then the proof is done. But it proves that we could dispense with the 1 cent coin and work with just, and add a 3 cent coin without missing a lot. Okay, so that is a proof that we can form all sums of coins greater than or equal to 8 cents with just 3 and 5 cent coins. Okay, so now we have another proof to work with. Let's see. Called the sum of a geometric sequence. Quiet. So the sum of a geometric sequence. Let's see. Actually, I'm not sure we're going to go on to this one right now. We've got about a half an hour, and I've got 2 proofs of a sum of geometric sequence to do. So what I think I'll do is another homework problem instead, and we will do the sum of the geometric sequence next time. I want you to get used to the process of a mathematical induction proof. That's the more important thing right now. So let's go back and look at some homework. So we did number 12. Number 13 and number 14 are related to what we were doing with number 12. They're talking about changing coin values and what we can model with that. Number 15 is the sum of squared integers. So let's try that. So number 15 it says prove that for each positive integer n, where n is greater than or equal to 1 squared. I wonder why. Plus 2 squared plus 3 squared all the way up to n squared. Sophus, stop. Equals n times n plus 1 times 2n plus 1 all over 6. Now we can check this to see if this makes any sense. If we start out with, say, 1 squared, and we put 1 in for n, we've got 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. That's 1 times 2 times 3, or 6 over 6, which is 1, so that works out well. So it seems to be working there, because 1 squared is 1. And then 1 squared plus 2 squared. Well, 1 squared plus 2 squared equals 1 plus 4, or 5. So what we have on the other side should equal 5 as well. So that would be 2 times 2 plus 1 times 2 times 2 plus 1 over 6. This is 2 times 3 times 5 over 6. And 2 times 3 is 6, so we would get just 5, which is what we wanted to. So this is looking pretty good. It looks like this is probably true. And in fact, it is true, but we need to prove it.
I prove it, it's true. That's it, my proof.
That's a statement, not a proof. Okay, so proof. We start. Sophia, stop. Sit or get out. So a proof by mathematical induction.
You've been going to the bathroom a lot. What's up?
So our proof by mathematical induction. First we establish what our property is. So let P of n be the property that 1 squared plus 2 squared plus 3 squared all the way up to n squared equals n times n plus 1 times 2n plus 1 over 6 for all. And here it's given that n is greater than or equal to 1, so we can say for all n element of the positive integers, and that will give us greater than or equal to 1. So there we've established our property. Now we need our basis step, so we say show What value does n take for our basis step in this case? What is our first value of n?
1.
That's right, 1. So we need to show that P of 1 is true. So, the left-hand side of our equation is 1 squared, which equals 1. The right-hand side of our equation is, give ourselves a little bit of room, it'll be 1 times 1 plus 1 times 2 times 1 plus 1 over 6. This equals 1 times 2 times 3 over 6, which equals 6 over 6, which equals 1. Then we can go on to say, leave that alone. Leave it alone now. Since 1 equals 1, P of 1 is true. So our basis step has been proven. Now we assume that it is true for the kth term. So now we show that for all k element of the positive integers, if P of k is true, then P of k plus 1 is true. So it's quiet. So now, to start off, we assume for all k elements of the integer, the positive integers, we assume that 1 squared plus 2 squared plus 3 squared all the way up to k squared. Notice that we use n at the very beginning and then we use k's. We can't use the same variable there. We need to use a different variable to establish the property and then to show the mathematical induction. So this is k times k plus 1 times 2k plus 1 over 6. So that's our assumption. We must show that it is true for k plus 1 squared. So now we can say this part right here, I'm going to mark this off on the side. This is the inductive hypothesis. So when you say this is done by the inductive hypothesis, this is what you're talking about right here. When you make that assumption, that part is your inductive hypothesis. So now, then, well, let's look at the sum of the first, the square of the sum of the first k plus 1 term. So we've got 1 squared plus 2 squared plus 3 squared. Keep going up to k squared and beyond to k plus 1, but watch your parentheses, k plus 1 squared. Well, notice that we've got this right here. That's the sum of the squares of the first k terms. And by the inductive hypothesis, we know what that is. So we can do a substitution using the inductive hypothesis. So we can say that this equals k times k plus 1 times 2k plus 1 over 6 plus the k plus 1 squared term is still there. And this is by the inductive hypothesis. That does not look good. I need to give myself a little more room. I think I do. Okay, give myself a little more room. We'll say this is by
We squeezed up hypothesis.
the inductive hypothesis. But notice now when we're dealing with this, we still have our k plus 1 squared term. Now, our first term on this right-hand side is a fraction over 6, and our other term is k plus 1 squared. We want to be able to relate these two things, but we can't quite yet. What do you think we should try? So one of the things is mathematical induction is often a method we're just trying things to see what's going to work. How can we relate these two things together? What should we try? We have a fraction and something that's not a fraction. Why don't we make our thing that's not a fraction into a fraction over 6? Because we know in the end, we know where we're going. That's a nice thing about mathematical induction. We know where we're trying to end. So we know that we want to end with k plus 1 times k plus 1 plus 1 here. And then a 2 times k plus 1 over 6. We know that we want everything over 6. So it's probably not such a terrible idea to go ahead and we can multiply this by 1, which is 6 over 6. So we can say this equals k times k plus 1 times 2k plus 1 over 6. This is plus 6 over 6, k plus 1, and we can think of this as k plus 1 times k plus 1 because that's the definition of squared. So we've just used definition of squared, and by the definition of squared, and basic algebra. Okay. And now we can join them together as one fraction, albeit a long one. Yeah. Plus 6 times k plus 1 times k plus 1. And then once we've done that, and this is just by basic algebra, once we've done that, we can notice, well, we've got a k plus 1 here and we've got a k plus 1 here. So we can join these two terms together using the distributive property.
No, I think it's the commutative.
No, it's the distributive.
Shoot.
So if we take everything we can take our k plus 1 out, side and front, and then we have the rest of the things. So we've got this k times 2k plus 1. Stop playing with things with your feet. Plus 6, and we have 2k plus 1s over here, but we're only using one of them with the distributive property, so one of them stays behind. K plus 1. End parentheses. All over 6. Well, how is this looking for where we're trying to go? We know we're going to go to k plus 1 times k, it will be k plus 2 times k plus 1 plus 1 over 6. And here we've got this part, and this part, and this part, and this part are the same. So somehow we need to make this thing here look like this over here. Well, rather this look like this. So let's get rid of all these markings. So what can we do? Well, let's multiply our k through the parentheses here. Oops, wrong thing. Let's multiply our k through the parentheses here and our 6 through the parentheses there and see what we come up with. And see if it gets us any closer to this.
The computer's freezing a lot.
Are people seeing what's going on, or is there a network issue? Yeah, I see it.
I'm seeing fine.
Okay, because sometimes my screen is going blank over here, it looks like.
Blanky, blanky.
Okay. All right, so we're going to keep our k plus 1 out in front, because we know we want that for later. And then we're going to multiply the k through 2k plus 1. That'll give us 2k squared plus k. Now we're going to multiply the 6 through the k plus 1. That gives us 6k plus 6. This is all over 6. Well, we can combine our terms here. We have a k and a 6k inside there. Sophie, stop wiggling around on your chair.
I'm trying to move the map thing back.
No, Sophie. So this equals k plus 1 times 2k squared plus 7k plus 6 over 6. Again, we're doing all of this by basic algebra. Now, we know that we've got 2k squared plus 7k plus 6, and we are pretty sure that that should equal our, what is it, our k plus 2 times 2 times k plus 1 plus 1. These should be equivalent. But we need to make certain that's the case. So we can, and if they don't, if they're not equal, it probably means we've made some sort of mathematical error. So it's a really good habit to get into to check and make sure that you are doing something that makes sense. So we've got, so remember how I was talking about the synthetic division and that we actually do it a lot, but we don't necessarily have it show in the proofs because we're doing it on the side. So 2k squared plus 7k plus 6. And into that, we should be dividing, well, we know k plus 2 should be in there, and if we've done it right, then we should be able to get the other value out right up here. So what do we multiply k by to get 2k squared?
2K.
2k. So we're going to line that up with our 7k here. Multiply this by 2k. So k times 2k is 2k squared. 2 times 2k is 4k. This is a plus and this is going to be a plus. But now we're going to subtract it. So we subtract 2k squared, subtract 4k, and our 2k squared is going to cancel out, and we've just got 3k bring down the 6. So this is 3k plus 6. Now what do we multiply k by to get 3k?
3.
3. So this will be plus 3. And when we multiply them, we'll get minus 3k minus 6. And because we have no remainder here, that means we've done it right. Now, the next question is this the value we wanted to get? Is that equal to what we wanted? And the well, actually it is. We just need to change it a little bit because what we had, the other value we were looking for was 2 times k plus 1 plus 1. If we multiply the k through here, that's 2k plus 2 plus 1, which equals 2k plus 3. So this is exactly what we want. So we have shown that k plus 2 times 2k plus 3 gives us this 2k squared plus 7k plus 6. So, and that is again, we can say we're doing that by the distributive law. You sort of do that on the side, but you just make sure that everything is working out. Okay, so this is k plus 1 times k plus 2 times, we had 2k plus 3. And this is over 6. This is still by basic algebra. And I'm going to erase this because it really shouldn't be over here. It was just, I was using it as scratch paper. Okay, and now I can say, well, this is the same thing as k plus 1 times k plus 1 plus 1. Let me give myself enough room for another parentheses. K plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. And this is all by, oh, excuse me, by
Basic algebra.
basic
Algebra.
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 And then this is actually where we wanted to go, so we can say this is what was to be shown.
Tiny square. Yep. Tiny square. Tiny square.
Oh no. Oh, excuse me. To be shown.
Tiny square.
And then, yes, tiny square.
My favorite.
Okay. So that is a proof that the sum of the squares of the first n integers equals n times n plus 1 times 2n plus 1 divided by 6. And then you know that this is true. So if you have some ridiculous number of integers that are squared that you need to add up, you can then use this formula because you know that this formula is true. Okay, so this is the process of mathematical induction. I'd like you, for the homework, we haven't done the sum of a geometric sequence. So we've covered the information for 1 through 5 in the homework, and proofs after that, so 12 on, you could also do. I'd like you to try to do at least 2 mathematical induction proofs. And in the next class, we will do 2 proofs of the sum of the geometric sequence. So that will cover 6 through 11. And then we'll also try more mathematical induction proofs. Okay, are there any questions? So it's all, keep in mind with a mathematical induction proof, there are steps. You always go through the same steps. First, you say what the property is, the establishment of the property. That's up at the very top. Your basis step. You show that the property is true for the first value that n takes. The second step is you assume it's true for the kth value that n takes. And then you use that, and that assumption of truth leads to the inductive hypothesis. You use the inductive hypothesis to show that it is also true for the k plus first value of n. And in that way, you show that for all values of n, your statement or your principle is true. So that's mathematical induction. It's very powerful. It proves an infinite number of things when it goes ahead and does it. But it's also thought of as one of the lesser proof methods. So are there any questions at this point? No? Okay. So try to do some mathematical induction proof. Also use some of your sum of the first n integers to show what values are. And we will meet again next week. Sophus, you have a question?
Didn't you say we were going to do the binomial theorem?
We are not doing the binomial theorem until you guys are used to mathematical induction, because the proof of the binomial theorem is incredibly difficult. And until you're used to looking at mathematical induction proofs, you will not be ready to look at... Stop making faces at yourself.
I'm making faces at the screen because I'm trying
Nobody in the screen can see you. They can only see the screen. The proof of mathematical induction, until you're used to the process of it, there's no point in showing you something as difficult as the binomial theorem. So first I need you to get used to that.
Sorry. My homework.
Okay. All right, so I'll see you guys next week. Thank you for joining us.
Bye.
Thank you.
Bye.
Bye, Joey.
Bye.